Lab 2, Motion of a Falling Object by Will Brantley. Introduction and purpose. For this experiment, we were supposed to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. Somewhat slowly means more slowly than a rock dropped from rest. Then we were instructed to produce 3 position versus time graphs. The purpose of this lab was to determine and understand the effects of gravity and drag forces on falling objects. So Newton's second law. His second law defines a force to be equal to the change of momentum with a change in time. Momentum is defined to be the mass m of an object times its velocity. So F net equals change in p over change in t, and then p equals mass times velocity. This is my tracker data. I dropped a white ping pong ball from 74 inches. It's basically my height. And this is the graph it created, and then this is the data I used. The tracker video of the ball falling will be put in the description. And then this is the glow script code for the predicted motion with just gravity. The ball's mass is 2.7 grams. And then the weight equals negative gravity times mass times j hat. And so the net force is just weight because there's no drag force. And then this is just the code to create the model. This is the model motion, the position time graph, and the velocity time graph. Just force of gravity acting down upon the object. So now we're going to add the drag force into the model, and drag force is the resistant force caused by the motion of a body through a fluid, such as water or air, so in this case air, and then a drag force acts opposite to the direction of the oncoming flow velocity, obviously. So this is the glow script code for gravity and drag force. Mass is the same, initial conditions are all the same, but we just add the constant for the drag constant, which is 0.001, and then the drag force equation is the constant times the magnitude of the velocity squared times j hat. And then the net force is just weight plus drag, because those are your two forces that are acting on the object. And then I just scaled the arrow so you could see each force acting upon each other. So you see drag's acting up against the object, gravity's acting down, and then these are the velocity time and the position time graphs. And so then finally I took all that data into Google Sheets, created a line graph with 3 different lines, and then you can see that the position without drag is the lowest because it has no forces acting up on the object, and then without drag is the closest to the end position of our experiment, but still my experimental position, as I talk about later, it can be improved if I had to do the lab again. So conclusion, what does it mean? Terminal velocity happens when the force of the drag is pointing up has exactly balanced the force of gravity pointing down. When this occurs, the net force is 0, making the time velocity graph slope would have to be 0. Therefore, if you look at both my velocity graphs, there's no slope of 0, so we know that this is not the case. What if this were to, since the drag force is proportional to the speed squared, the magnitude of terminal velocity will not change. And then I touched on this earlier, but looking back, how can I improve? I think I should use a larger object with more surface area than a ping pong ball, and maybe a brighter colored object so it's easier to spot when I'm doing the point masses and tracker, and then just cut down on the lateral movement and initial speed of the object.